shove it all back in.
Did you, is it okay if we wrote our name on the front page? Did you want us to write our name on the front page or?
No, just inside on the.
Inside on the actual paper?
Yeah.
Right, okay.
No, thank you.
Do you want it in the envelope or is it okay?
Doesn't matter. Yeah, I need your number here, right?
In addition to the name on the inside?
No name, just the
I didn't
numbers.
write- I didn't write mine on the outside.
Okay. Yeah.
So you need the name here?
That's fine, yeah, but I need the number outside.
Outside?
The number next to the
You have to
staple.
put it here.
Which one? I think this is probably it. Yeah.
I had to borrow it.
Oh, okay, never mind. I just didn't know where it was.
Okay. That makes it easier. All right, there you go. Thank you.
Thank you.
Thank you. Wonderful. Great. Okay. Okay, thank you. As if I don't have enough to do. You give me a sign, it's not. Do you have any questions for me before I get started with the lecture? Any questions? Okay, well, last what we've done was we were solving the wave equation for the waveguide, and we started with Maxwell's equations, and we decided we were going to work with the point form. Let's see here if we can remember all the constraints or the special things that we assume. We said it's a point form, means we end up with differential equations. We work with one frequency, that was harmonic analysis. And we did the expressions in the frequency domain, phasors. We assumed uniform cross-section. What else did we assume? Homogeneous media. Source free. Lossless. Otherwise ideal. Dale. Do you recall any other constraints that we take into account? When we said uniform cross-section, we're assuming here one direction, not one direction, what is it? One dimension, propagation? It's not proper, no. Along the z-axis, I guess that's how we wrote it, right? Yeah, I guess we wrote it that way. Along the z-axis, you have uniform cross-section. So when we said that, we are assuming that we have a guide we have other discontinuities which were outside the domain of analysis, so we are only analyzing this part. We're analyzing only the part away from discontinuities, the straight sections. Sometimes we refer to that as straight section. No bends, no twists, no nothing else but the guide itself. That kind of analysis so far can apply to transmission lines, to waveguides, metallic, dielectric, right? Because we have not imposed any boundary conditions. When you put your boundary conditions, you specify. So actually this can also be propagation open space, right? But it's not any kind of propagation open space, it's this kind of propagation open space, which is along one dimension. Right? And we end up with del squared E is equal to minus omega squared mu epsilon E, or the del squared H, right? Same thing. So you can put that like that. You can put this like that if you wish. Either equation is added. These came from Maxwell's equations, so we better write those on the side. Curl of E is equal to, this was Ampere's law, J omega, wait a minute, that's the Faraday's law, minus J omega mu H. And H, that's Ampere's law, which is J omega epsilon E. We're ignoring the J here because it's source free. J is equal to 0, source free. Now we need to solve either of these, not both. And the reason for that is there will be some redundancy here. And we said we prefer to work with the E because of psychology and background and all that. And if we solve here for the E, how do we get the H? If you solve the other one for H, then you add more constants in your equations. You realize that this is a second order differential equation, and when you integrate, you end up with a few constants. So you don't want to solve another second order differential equation here while you have the first order there that can help you out. If I get the E, I can get the H right there. So actually, it's just like when you have two simultaneous equations, equation 1 and equation 2, and you reduce both of them to an equation 3, which is dependent on both, right? You need to go back and use one or the other of these two equations to finish your job, right? Like if I say x plus y is equal to 2, and x minus y is equal to, let's say here, 0, okay? And if I solve, what do? I add them up. So I end up with 2x is equal to 2. That means x is equal to 1. How do I get the y? You go back and use any of these to get your y. X is equal to, when you put it there, you get the y. When you put it here, you get the y. So the combined equation and one of the originals would be adequate. So we're going to choose this one here and that one. I solve this and that in combination will get me the final answer. All right, so work on this one here, and we said E is simply EX, AX, plus EY, AY, plus EZ, A sub Z, and we chose Cartesian coordinates because we are headed towards the rectangular guide. If I'm working towards the cylindrical guide, or actually called circular guide, then we would use other forms like cylindrical coordinates. So that means you can just use that, so you end up with del squared EX EY EZ is equal to minus omega squared mu epsilon EX EY EZ. And any of these we can work on, so we chose to work on the EZ first, right? Eventually we'll work on all of them, but just start with one. So we said del squared EZ minus omega squared mu epsilon EZ, and we use separation variable where we assume E sub z of the form of fx function of x only, fy function of y only, fz function of z only. We put that in, we ended up with fx double prime over fx function of x only here, plus fy double prime over fy function of y only, plus fz double prime over fz function of z only is equal to minus omega squared mu epsilon. And we said that this is a constant. Actually, we call it minus k squared. So from there, we concluded that each one of those must be a constant in itself. So we call this one here minus kx squared, minus ky squared, minus kz squared. And that's where I wanted to make sure that I am in compliance with my notes in this regard. And that would be, yes, that's how my notes go. Okay? So, we solve every one of these separately. So we have three functions here that we need to solve for to get the E sub z. I need to get each one of these multiplied by each other. And these are all similar functions, and we chose them as minus kx squared, and we said they really can be chosen any other way, and the end you will find the right answer, whichever way you start. These are all assumptions, but they don't influence the final form. It's just a convenience that we chose them that way. So this one here solves as fx is equal to, we can use either sines and cosines or exponential of j's, right? You can say e to the j kx x, and if you differentiate that twice, you end up with minus kx squared e to the jx jkx x, right? So here it is, you know, second derivative gives you minus kx squared, and that's really what you want. Second derivative gives you minus kx squared. The other option is if you assume a cosine kxx or a sine, either way, and this also plus or minus here, it doesn't matter. Both of them will give you the same exact answer. You differentiate twice, you end up again with minus kx squared times cosine or sine kxx. So you can see whichever form you use, you'll end up with the right answer. For, again, convenience sake, I'm going to pick the sines and cosines. So I'm going to write this as a cosine kxx and a sine kxx. Now, when you have two possible solutions, and that's a rule in solving differential equations, you look at the general solution as the superposition or the linear sum of the two possible solutions weighted by a certain weighting factor. And the weighting factor that I used here is, let me see my notation, so we'll be consistent. I use F1, F2, F3 rather than Fx, Fy, Fz, by the way. And what kind of notation did I use for the constants? I used F1 sub c, which is a constant. I use here F1 sub c, right? The c here refers to a constant. And I use F1 sub d plus F1 sub d. These are my notation for constants. I didn't want to use A and B and C and D and all that for some reason. I'm still thinking about what is the proper notation here. Right, so these are constants, constant coefficients, right? In other words, don't know how much of a cosine or how much of a sine, so I just put some weighting factors and let the boundary conditions decide for me if one of them is 5 and the other one is 2, right? Whatever it is. So that's your fx function. Your fy, I'm going to write it the same way, so it's going to be f2 c cosine ky times y plus f2 d sine ky times y. And the third equation, I'm going to use a different color for that because there's always something unique about the z direction. It's different than the x and y. X and y are the cross section, and the z is going to be the direction of propagation. And again, looking ahead, I know along the direction of propagation I expect to use, or better use, exponentials. So I'm going to use exponentials here. Like I said, either one will give you the same final answer if you just do a bit more math manipulation. So f sub z is going to be f3c again, and then have e to the minus j kx kz times z plus f3d, that's a 3, e to the plus j k sub z z. Here are my 3 functions. All I need to do now is combine them all in here, and I have e sub z. So let's write e sub z now. I still yet to get ex and ey and hx and hy and hz to get a full solution. I have 6 field components, right? So e sub z now, well, it's the vector component, e sub z, is a product of all these 3, so I have one for the x, one for the y, and one for the z. This one here is f1c cosine kxx plus f1d sine kxx, the same, right? I'm going to write f2c cosine k sub y plus f2d sine the same. And f sub 3c e to the minus j k sub z z plus f3d e to the plus j k sub z. Following that? Like I said, I'm going to send you those few pages of the notes. I've got about 20 pages. And right now we are on page 7 or so. Actually 6. Okay. Meanwhile, I need to keep in mind that these three constants are constrained. They just don't go any number on their own. There is some relationship, kx squared plus ky squared plus kz squared equals to k squared, which don't forget that this omega squared mu maximum. Frequency dependent, material dependent. Okay. That's as far as I can go without applying boundary conditions. I have a solution for E sub z. I can also write a solution for E sub y and E sub x likewise. And I can write the other ones, but they will all have different constants. So I better determine or eliminate or reduce the constant format first before I add more constants in my equations. If I write the other ones, this one has how many constants? 1, 2, 3, 4, 5, 6, 7, 8, 9 constants. Well, actually, that's an equation here, so that reduces number of constants by 1. So that's 8 constants, right? If I work with 8 constants and I add the E sub y and the E sub x, these will add probably 6 more constants, right? So that's now 14, and you know, things will accumulate. So better start looking at the boundary conditions and reduce the number of constants before I add any more. So we're gonna now specify that I'm working with a rectangular waveguide. At this point here, I'm gonna specify working rectangular, metallic or conductors. Waveguide. Okay, so we're going to have this waveguide in rectangular format. I'm going to lay it on my XYZ coordinates, and usually we choose the broad dimension on the X direction and the narrower dimension on the Y. And the size here is going to be labeled A, and the size here is going to be labeled B. These are standard notation that you'll find everywhere. And if this is your X and Y, then obviously your Z is coming out of the board. And we're assuming that these are ideal conductors. So I'm going to give them a distinct color here, red color. Ideal conductors. And when you have an ideal conductor, the filling will be ideal dielectric. So that is epsilon here and mu. And sigma is 0, right? These are the properties of the dielectric inside, while the conductor, obviously, sigma here is going to be infinity. Right? That's what you get for the conductor. Perfect conductor, infinite conductivity. Boundary conditions between dielectric and a conductor. When you have a dielectric and a conductor interface, the tangential field component is 0. You remember that? Because conductors are equipotentials. The potential here is supposed to be the same, so the gradient is 0. So E tangential is equal to 0. E is allowed to be only normal. So E tangential on this side here, okay? Which components are tangential? Let's use a blue color here to identify which components are tangential. This is tangential here, right? This is tangential there. It's also tangential here and tangential there. All these have to be zeros. 0, 0, 0, 0. Also, D subtangential. So all these components, if you wish to put them, I'm going to put them as dots or crosses, doesn't matter because they are zeros anyway, right? On all four sides, the tangentials are zeros. So which components are now marked in blue? E sub x, I'm sorry, E sub z, okay, at E sub z at x is equal to 0. To 0. E sub z at x is equal to, I'm sorry, this one here, x is equal to 0. So E sub z, which is these dots here, right? The dots here, these are E sub z's. Okay? E sub z here at x is equal to 0, 0. E sub z at x is equal to a 0. E sub z at y is equal to 0 is 0. E sub z at y is equal to b is 0. The arrows now. E sub x, this arrow is E sub x. At y is equal to 0 is 0. And E sub x at y is equal to b is 0. And the vertical arrows, E sub y at x is equal to 0 is 0, and E sub y at x is equal to a is 0. Right? These are all the tangential fields. I'm interested in these at this point, right? So I'll just focus on these. These I can delete them later. I don't need them now. So I'm going to use these first. These are the E tangential boundary conditions. There are other boundary conditions I can use. But for now, we just focus on E sub z. Because it's the tangential component. So I'll go up there and put x is equal to 0 and equate that to 0. Right? So do them one at a time. Can we just do them on the board here without writing much? If you be attentive for this discussion here, it will help. And look at the board. Okay, we'll start putting x is equal to 0 and equate that to 0. X is equal to 0, that means I put a 0 here and a 0 there. Right? And put a 0 here. What's left? This f1d is sine 0, which disappears. I have f1c times 1 is equal to 0. So I end up with f1c times 1 here is equal to 0. And this gets multiplied by the other brackets here for the y and the z, which don't really matter because all that I get here is f1c is equal to 0. Right? Is that obvious? Are you guys following? I get f1c is equal to 0 if I do the direct substitution of that. So this one gives me f1c is equal to 0. I get rid of one of the constants. Likewise, I'm going to do this one here now. Let's use a different color. What color do I have? Okay. Use this one. We'll put y is equal to 0 now. So I put a 0 here, a 0 there, and a 0 here. F2C cosine 0 is F2C. Plus, that's a 0. This bracket stays as is, and this one stays as is. So I end up with F2C times 1 is equal to 0 on the left here. So I conclude that F2C is equal to 0. I got rid of two constants. Wonderful. Hope we can get rid of more. So I'm going to rewrite my equation now without these two constants, if you don't mind. So I'm going to make that disappear here. Just going to relabel this as F1D sine, and make this F2D sine. KYY. Okay? Now, I soon recognize that F1D and F2D are multiplied by each other, which I can combine them into one constant, right? Do I need to know each individual one? No. In fact, I can actually multiply them through here and get rid of them completely. So now I'll call this one F4 and combine these two. So I get rid of two constants because I don't need those coefficients separately. Now let me make sure that I'm using the same notation here. What did I call this combined constant? I guess I recognize now at this point that this is actually an electric field. This coefficient here now have the same units as electric field, right? So there is no need to call it anything else but E now. So I'm going to call this E, and I'm going to call this E. And we know from history that when you have a negative here that you can call this a plus and you can call this a minus. E sub z plus and E sub z minus. So I'm combining the constants all in one, and they have the units as electric fields, might as well call them E, and they're components of E sub z, so I'm going to refer to them as E sub z's. And the one with the negative in the exponent is actually a wave that travels in the positive z direction. We've seen that before. I'm going to show it to you again now. So we'll call it plus, and the other one called minus. So what do I have now? I'm just going to erase all this now. This part have been used. No. I still have this one now. E sub z at x is equal to b, x equal to a, 0. Haven't used that one yet. I just use those. So now my E sub z is equal to sine kxx sine kyy times E sub z plus e to the minus j k sub z z plus E sub z minus e to the plus j k sub z. Okay? Now, let's work with these two boundary conditions. See what can we get. I'm going to work with this word here. So I'll put x is equal to a and equate that to 0. So I have 0 on the left hand side is equal to sine kx a sine ky y times whatever the z term is. That means this must be 0. Sine kxa equal to 0. That means my kxa is equal to multiples of pi. That's the sine function, right? It becomes 0 when you have multiples of pi there. That means my kx is m pi over a. In other words, 0, pi over a, 2 pi over a, etc., right? Done. Each one of these boundary conditions is giving us some more information and reducing the number of unknowns in our equation. Likewise, if I do the other one, I'm going to check mark here, and I'm going to write the ky as n pi over b. It's obvious, right? 0 pi over b, 2 pi over b, etc. So it looks like the kx and the ky are not single valued. There are lots of potential or possible combinations of the kx and the ky. And that's given by the m and n. M here could be 3, and n there could be 2, or here